Good day and welcome to this discussion on Unit 5.6, which is on the transformation theorem. In the previous section, we discussed polar coordinates, which is just a special case of transformation. We have seen that the transformation to polar coordinates can be very useful. For example, the region R in the first quadrant between the circles x squared plus y squared equals 1 and x squared plus y squared equals 4 is transformed to a simple rectangular region D, where D consists of all points r, theta, with r between 1 and 2 and theta between 0 and pi over 2. Let us observe what we have in this situation. The first thing that we note is that the region R in the first quadrant is a closed and a bounded set. We also note that if R subscript 0 is the interior of the region R, that means R without its boundary points, then R subscript 0 is an open set since it does not contain any of its boundary points. We also note that the equations that we use for polar coordinates, namely x equals r cos theta and y equals r sin theta, actually defines two continuous functions x and y from the region R into the real number system. Calculations show us that the functions x and y both have continuous first-order partial derivatives on R0. Therefore, the expression j brackets r comma theta, which is defined as a determinant, makes sense. As you can see, it turns out that j r comma theta is equal to r, and r is not 0 on R0, which is the interior of the region R. The expression j brackets r comma theta is called the Jacobian of the transformation. So, if f is a continuous function defined on the region D, then by theorem 154, we get that the double integral of f over the region D is equal to the double integral over r of f at r cos theta, r sin theta times r, the Jacobian. But what about other regions? Are there perhaps other transformations that can simplify double integrals? Let us consider, for example, the region in the first quadrant enclosed by the parabolas y equals x squared, y equals x squared plus 1, y equals 1 minus x squared, and y equals 2 minus x squared. It would certainly help if we can transform this region into something a bit more familiar. Fortunately, there is a general transformation theorem which is given by our theorem 162. As you can see, the conditions of theorem 162 is exactly what we highlighted in our previous example. We start off with a set R that is closed and bounded. It consists also of an open set R0, the interior of R, together with its boundary points. Furthermore, we assume that we have two continuous functions of R, u and v, that is the functions x and y, that have continuous first-order partial derivatives on R0. We also assume that the Jacobian of this transformation, which we denote by j brackets u comma v, defined by the matrix that you can see there, is not 0 on R subscript 0. The general transformation theorem then tells us that if D is the region onto which the region R is mapped, then the double integral over D of f at xy will be equal to the double integral over R of f at x u comma v, y u comma v, times the absolute value of the Jacobian dA. Before we do an example, there are two very important remarks that we need to make. The first one is that when applying theorem 162, it is often more convenient to give the transformation in the reversed order. That is, we give u as a function of x and y, and v as a function of x and y. In some cases, one can then algebraically manipulate these equations to express x and y explicitly in terms of u and v, so that it fits the requirements of Theorem 162. But this can often become complicated. An alternative approach in such cases is as follows. We calculate the Jacobian j x, y, and if that is not 0, the transformation is invertible, and we can find the Jacobian u, v by taking the reciprocal of the Jacobian j x, y. The second observation is that it is sufficient to express the boundary curves of the region D in the xy plane in terms of u and v. The corresponding curves in the uv plane give the boundary of the transform region R in the uv plane. All of this becomes clearer when we do an example. We will demonstrate the use of Theorem 162 and the remarks we made in 163 with the example above of the region between four parabolas. We will calculate the double integral over R of x dA, where R is the region that we previously described. We first rewrite the equations to get the following equations. Y minus x squared equals 0, y minus x squared equals 1, y plus x squared is 1, and y plus x squared is 2. If you have a look at that, it makes clear that defining u and v as u equals y minus x squared and v equals y plus x squared as a good proposal for a transformation. We can see that the functions u and v are continuous, and they will have continuous first-order partial derivatives, since all of these are polynomials. In terms of Theorem 162, however, this is a transformation in the reversed order. So we calculate the Jacobian j x, y, and as you can see, it turns out to be negative 4x. Since x lies in the interior of R0, we know x is not 0, so negative 4x is also not 0 on R subscript 0. By the remark in 163, we now know that the Jacobian u, v is equal to the reciprocal of the Jacobian x, y, which means it is equal to negative 1 over 4x. It is clear that the curves that bound the region D are given by u equals 0, u equals 1, v equals 1, and v equals 2. So the region D is the set of all points u, v, such that u is between 0 and 1, and v is between 1 and 2. We can now apply Theorem 162. So the double integral of x dA over R becomes the double integral over D of x times the absolute value of the Jacobian, which is negative 1 over 4x dA. Keeping in mind that the absolute value of x is equal to x when x is positive, we can simplify this double integral over D to the iterated integral a quarter times the integral from 0 to 1 of the integral from 1 to 2 of 1 dv du. Calculations of these integrals leads us to a final answer of a quarter. That concludes this discussion of Units 5.6. There is a very good example in the course notes that I strongly recommend you work through, and also work through the exercises. Goodbye and good luck.